Okay, what am I going to talk about today? I have come to some conclusion as to what I wish to talk about. Obviously, risk and uncertainty in wind engineering is inherent to the game. That's always going to be there. Some design processes treat risk fully through risk analysis. Others, design processes, tend to rely on what you might call limit values of different types. This presentation is frankly an exploration of my own of the relationship between risk and limit-based approaches, and I'm going to illustrate it through a range of applications. It's very provisional thinking. I'm working on the basis that you're a kind audience out there, and I hope you don't disappoint me. These are really some thoughts I'm having at the moment, some ideas about where work might go in the future. The context, I'll give some sort of generalized framework, then I'll go through a series of examples, and these examples are basically things from my own experience, really. Coming on to talk about risk and limits, and I also want to talk about the consequences of failure of systems as well, and end with some concluding thoughts. So, a generalized framework, let's start with that. This is a key diagram, really. When we go through a design process in wind engineering, industrial aero, we start with some sort of stressor and we start with some sort of strength of the system, and they're both usually probabilistic. The ideal is to put them together, and where the probability distributions overlap, that enables us to get some idea of a risk of failure. So that's for the system, but then we probably need to think about the operation of the system as well, and the consequence of the failure. And if the consequence of a system failing is unacceptable, we can do one of three things. We can change the strength of the system somehow. We may be able, in a position, to change the stress applied. And we may be able to change the operation. So keep that sort of generalized framework in mind, because I'll be coming back to it. The classic way, the most explicit way I've seen this done recently has been by some colleagues at SNCF, the French National Railways, who've looked at the effect of ballast flight underneath trains. When trains go above a certain speed, ballast tends to take off and it can do a lot of damage. And there are some pictures. That rather boring picture on the top right is just a high-speed line in Britain. It's just a track with a hole in it where a bit of ballast has been ground down between the rail and the wheel. And when that happens a lot, that's actually quite expensive to do the maintenance on it. And there's some experiments we've done on high-speed lines as well. And SNCF have actually used this sort of approach quite fully. They've looked at the probabilities of underbody flows, they've looked at the probabilities of track strength, they've got a risk function for ballast liftoff, all probabilistic. They put that together with some knowledge of the service level and the weather, and looked at the severity of an incident. And then they have actually three possibilities. If it's really bad, they can change the train geometry to change the airflow under the train. They can change the strength of the track by doing something with the ballast. Or, as they mainly do, in fact, is just they change the service level. They reduce train speeds when there are issues forecast. And that's a nice way of the entire system that's been put together. But perhaps not terribly familiar to most of you. Most of you know a bit about structural design. Structural design usually calculates a designed wind speed at a specified risk. Using wind tunnel CFD data or pressure coefficients, you get a design load. And that structural design process then puts that load, seeks to design a structure that can withstand that. And we use code data, we use wind speed data, and that's a Eurocode picture there you've seen. Actually, the design process, when you look at it, is a very cut-down version of that generalized framework. You start from the design wind load and the structural design, you put it together based on some sort of criteria of risk, cost and use of building, and you then change the structural design and go around that loop until it works. But inherent in that, well, first of all, the criteria that we use are actually that they embed a knowledge of the risk of failure of the function of the function of the building. It's in a way a surrogate for consequence and operation. And similarly, the structural design has probabilistic information in there, but it's it's in there by way of partial factors as a rule. And the design wind speeds, again, is a way of encoding probabilistic information. So it's, if you like, almost a limit-based system, but inherent in it, implicit in it, is a lot of the bigger risk analysis there. If you look at something that I've spent a lot of time on over the years, the crosswind effects on trains. Trains do blow over sometimes. The design process is usually to measure the aerodynamic forces using wind tunnels and CFD, put those into some sort of model of the train behaviour, and you get what's called a crosswind characteristic, the accident wind speed against vehicle speed. And then that can be used in a statistical analysis of the site conditions to determine the risk and the consequences of an accident. And there are some pictures of trains that blow over or trains that are at risk of blowing over. I could talk about that at length, but I haven't time, of course. And the ideal system that's actually used when you actually want to do a full probabilistic analysis of that, you take aerodynamic force coefficients for the trains, you put them through some sort of train mass and dynamic model, you calculate a crosswind characteristic, then you think about operational risk and quantify injury and death. You can restrict the service, or you can, say, use fences to shelter the train and to reduce the stress. Or you might be able to change the train values, make it less prone to blowing over. In other words, you can increase the strength. That's if you're doing the full system. However, a train manufacturer doesn't want to do that. A train manufacturer just wants to get his train out into service. And they operate a very much reduced version of that system. They take the train aerodynamic coefficients and the train dynamics. They calculate, so the train aerodynamic characteristics might look like that. The train dynamics might be a 63 degree of freedom system. And they calculate a plot of accident wind speed against train speed. And that's as far as they go. Now, problem is there, in that case, they are all deterministic functions. They are not probabilistic functions. And the justification is experience suggests that those limits are adequate simply by experience. So a limit-based approach. Another one which is perhaps more in line with the sorts of things that Bert does here. In building design, of course, pedestrian level wind safety is important. Wind conditions are usually measured around wind tunnel models or using CFD and MET data to find the probabilities of different limits being exceeded, different wind speed limits being exceeded. My interest in this was brought about because of a huge building new building in Leeds in the north of Britain, north of England, that had severe wind problems around the base with people blowing over and finding real difficulty walking. But tragically, that happened. A lorry blew over around the base of a building and actually killed somebody and raised the profile very significantly. Now, again, the full approach, you start off with wind probabilities, you have some idea of human and vehicle stability probabilities, you calculate the risk of discomfort, maybe distress, you look at the operation of the area, and you look at the severity of the discomfort and injury, and then you can change the design or the shelter the design. You might restrict use in certain conditions. Some of you will know, you've experienced it. I've been playing around with doing a full risk assessment, and it gets complicated. And that's an important point. I put this up because it's complicated more than anything else. You look at the probability distributions of people blowing over, cumulative distributions. You convolute that with the probability of wind speeds, a viable distribution, and you get quite complicated looking integrals at the bottom of the overall risk. Now, hold on to that complexity. I don't expect you for a minute to understand that. However, in most cases, what you do is something like this. You take the wind probabilities that you get from wind tunnels, CFD, whatever, you apply them to comfort and distress limits, and you say, well, that's okay, or that's not okay, and then you do something about it. You change the design or shelter or restrict the use or something like that. And those comfort criteria again, they're a surrogate. They're a surrogate for human reaction, the use of the area, the consequence of discomfort and injury, and they're justified by experience, at least for comfort limits. When things get unsafe, it's a different matter. So, where do these thoughts lead me? Well, obviously, I think if you're in a position in design to do a full risk assessment, that allows potentially all aspects of the problem to be taken into account. And more importantly, it gives us a risk that's consistent with the other sorts of risk assessment that are done in other aspects of the design other than wind loading. So it can actually then be completely consistent with other ways of looking at the matter. Without doubt, this can be complicated. But I say it does allow a comparison of risk with other risks. The use of limit values, though, is actually really convenient. It's quite easy. But when you get to limits, I would like to make some points. The operation and the consequences of that operation are only taken into account implicitly in the use of limits. Most of the time, the uncertainties associated with the operation usually dominate the risk consequence calculations from the uncertainties from other sources. Now, that might be hard for wind engineers to stomach, that the risks they calculate are really irrelevant to the risks of operation, but most of the time they are. And as limits tend to be deterministic and can be treated as precise targets by designers, they can actually distort the design process. For example, and here, my apologies if I annoy anyone with these, I have known people do structural design codes, look at structural design codes, and actually note that if they move their building a bit so it's a bit further away or a bit close to the sea, they can get a significant reduction in the load by going into another category in the code. And they sort of look at the data for the most extreme high tide and then use that as their baseline. It's got no relevance to reality, it's just getting something through the code. Similarly, on trains, if you want to get your crosswind characteristic below a certain level, you might be able to tweak your train dynamic system. Again, that's great, it gets your train authorised. It's got no relevance to reality at all. And similarly, if you change your building design to meet your 5 metre a second comfort limit that you've got in Holland, then, well, that's okay, but when you look at things in big terms, it really isn't very sensible. And what's more, actually, when you're working with these design limits, it can result in an expectation that CFD and wind tunnel results have a much greater accuracy than is true. If you're trying to work to these precise limits, you want your CFD and wind tunnel to be really accurate. And those of you who do CFD and wind tunnel results know that you can't do that. You always have uncertainties there. So I just worry about the use of limits in some way. Come on to consequences. That's at the end of the chain. It's not something that engineers usually think about. How do you actually specify consequences? Maybe in terms of safety, maybe in terms of costs and benefits, maybe in structural design, maybe in terms of resilience and emergency planning. It leads to different sorts of design. These days, maybe in terms of the broader picture of sustainability, and there we've got the 3 pillars of sustainability, or more and more in urban design, people are looking at different future scenarios. How do you specify consequences? Lots of ways of doing it. They're just some of them, no doubt there are others. And the language or the specification of consequences is very different from engineering languages. They like my presentation so much at the front here, they're waving their programs about at me, the yellow ones. Almost done. How should engineering-based risk calculations be related to such specifications of consequences? That's not a question engineers normally ask. We don't like the fuzzy bit of the consequences. I actually think it's a question that's vital that engineers should be involved in. I don't think engineering should stop at the simple risk assessment. Philosophical point, maybe. So, some concluding thoughts. Maybe the general advice framework there is a contribution to the field of helping us think clearly about risks and consequences. Maybe not, you might say. An assertion, I would make the assertion that where possible a full risk-based design process should be used in wind engineering and industrial aerodynamics with the components as transparent as possible. A plea for the greater recognition of the limitations of limits, if that makes sense, and for their sensible implementation and use. And that all of us who are educators should actually get this through to our students, who, as one grows older, it seems to me that students become ever more deterministic rather than statistical in their thinking. And a suggestion. Serious work, I think, is needed on how risk assessment methodologies in our field actually interface with the calculation and the specification and the vocabulary of consequences. And there's a lot of work to be done there. And as we're in the Netherlands, ladies and gentlemen, I end with a picture by Van Gogh. Thank you.